Hello, everybody. I'm Ajay, your host today for this presentation. Would it be okay to jump in, or are we waiting? Is there a break?
No. The break will be after my presentation. So yeah, just continue. No, don't worry.
All right. Well, let me start by congratulating Grab's team for everything they have achieved, and I wish them good luck for next exciting features. Today, I am presenting on behalf of Accessa some work that we did, which was in collaboration with UPB from Bucharest, Polytechnical University. And a little about me. I'm working as a software engineer with Accessa. It's my second year at the company. And my roles usually include building Java microservices and doing research and development for the company. We have done research into distributed computing for over 1.5 years, and this was an interesting task where we wanted to classify some gossip and epidemic protocols, which are becoming, I mean, they're not becoming, they're important protocols when it comes to sending messages in distributed environment. And I think the distributed environment is heavily used in almost all the fields today, including the much increasing field of artificial intelligence. I mean, increasing in popularity. And this specific study was done together with Dr. Elena Apostol from UPB, who guided us through the classification. And my goal today is we published the article in today's software magazine, so it will be available soon to be read in details. But I wanted to touch some ideas from the study itself. Perhaps it generates curiosity. Perhaps you as an audience could connect with this, or perhaps there are some improvements that you think should be made in this study. So I'll start today with gossip protocols, just a brief introduction to see what they are, and then we will see how we ended up classifying them, some practical implementation of these algorithms, and a use case that we ended up using inside the company. So a little about gossip protocols. They were, I think the term was coined in 1987 by Dr. Ellen Digmers, who was researching some efficient algorithms to replicate databases. And their goals were for Xerox Corporation. They wanted to replicate around thousands different sites with an assumption that the network that connects them, it's unreliable. So the different replicas can drop down. And they wanted to come up with an algorithm that could that would make sure that there is consistency across each replica. And for this, they studied the existing uh, algorithm at that moment. I think it was direct mail. After which they researched two randomized algorithms in order to make sure, in order to optimize and provide more reliable results. And those algorithms were anti-entropy and rumor mongering. And the basic idea behind this was very simple. So whenever a replica of a database had a change, it would send a mail to every other available node in the network, right? So if the green changed, it would send a message to every other 3 databases in the network. And this was very unreliable because it was using mailing protocol in that period, which in itself was unreliable in practice, not in theory. In theory, it was a bit different scenario. Nevertheless, it also meant every change would generate at least m number of messages if there are m number of nodes. And if you had n number of changes, the volume of messages in your network would be very large. And this also implied somehow that you were connecting all the nodes with all the other nodes. So the amount of links in the network were also very large. Another implementation that they studied was anti-entropy, where they were selecting random pairs of databases, let's say in our case, green and yellow. And this green and yellow databases would change their entire state to compute deltas and then update their own state based on the deltas they computed. This provided reliability, but it was still an expensive operation to do because you are sending all the data through the, you have to exchange all the data in order to reach consistency. So they came up with the third idea, which was rumor mongering, and that also kind of gives the name to the protocols. It works pretty much like how a gossip would work or a rumor would work in real life. One person tells someone something and the other person that then passes on that rumor to the next person, right? And eventually we get bored of the rumors and they are not interesting to us anymore, so it stops spreading. And that was the idea. They considered any change in a database would become a rumor, and I want to distribute that rumor through the network. I have some hot rumors that are very interesting, so I will keep transmitting them whenever I meet a new person, and the new person would do the same. But eventually the rumor would become boring to me and I would discard it, right? And then I wouldn't transmit that rumor anymore. So these were the ideas, and rumor mongering as an idea provided a lot of benefits. It was very fast. It made sure that the messages were reaching to the edge of the network in a relatively faster time. But they had some issues, and that's what we discuss also in the paper. Different algorithms having different issues. What are the pros and what are the cons? With this overview of the gossip protocol from the beginning, let me take you more into how we ended up classifying them. So for us, there seemed to have emerged 4 criteria that we felt would justify classifying gossip and epidemic protocols. And first one was dissemination and aggregation. These are the algorithms that focus on either distributing the rumor or aggregating changes, right? So you have 2 sets of algorithms. One focus on optimizing the dissemination, like how efficiently can we spread the rumor. And there are others which focus on aggregating changes, where the focus is on efficiently aggregating the changes, not necessarily if it is efficient to spread the messages in this way. Second criteria was synchronous and asynchronous communication. This doesn't necessarily need more explanation. It is happening at the communication layer. So do we wait for all the other messages to be processed before we send our own message in synchronous mode versus an asynchronous mode where we don't wait? Then there is anonymous and non-anonymous communication, where in case of anonymous, we don't really care where the message is coming from. We don't know the identity of the senders. We don't know how many they are. Versus in non-anonymous, where we know which peers are sending us messages and we are aware of their identities. And lastly, error correction and no error correction. There are class of algorithms which don't provide guarantees that you would have strong consistency across your replication, right? There is always a non-zero probability. So that was the 4th criteria. I'll go a bit into each one of them and also show you maybe some algorithms that fall into these categories. So again, dissemination and aggregation, like I said, dissemination focuses on spreading the information. So in our example before, rumor mongering, where the idea was how efficiently we can spread changes throughout the network, versus anti-entropy, where we wanted to make sure that we get a stable aggregation. Our aggregations are done in the best possible way. so that we achieve consistency across our replication, right? And you have plenty other algorithms which sort of follow this idea, where wherever you end up computing deltas or optimizing the algorithm, keeping the data in mind, you end up adopting for aggregation. And in the use cases where you need stronger consistencies, you adopt aggregation. In the use cases where you are okay with eventual consistency or weak consistency, you go for algorithms that are in the category of dissemination. In the article, you find references to all the algorithms, so you can find more detailed information about them. Yeah, so the next category was synchronous asynchronous communication. Idea of synchronous communication is that you kind of define a bound, a time bound, in which we expect the transmission to finish. We will block ourselves for that time, and after that we'll time out the operation and move to the next one. Versus in asynchronous, where we don't have any time bound, and we can let the message spread in as much time as it needs throughout the network. And when you do that, you also need to take the responsibility that you somehow make your messages order. I mean, you should make the processing of messages order invariant. It shouldn't depend on the order the message is coming, or you must handle some messages coming out of order, or you must provide other guarantees from your asynchronous systems to bring total order. Nevertheless, there are benefits of synchronous algorithms, and asynchronous algorithms depends on the network that you are implementing the algorithms. And we felt that it is very important to mention, because once you solve, when you're solving a problem, you never solve the same problem, let's say, in the same network that you, I mean, you cannot generalize algorithms for assuming networks, so you must respect what kind of network you are running your distributed algorithm on. So that was an important criteria. Moving to the next one, anonymous and non-anonymous. There isn't more to add. As I said before, in anonymous, you would not require to be aware of identities, which was the case for us as well when we implemented in our internal use case. In non-anonymous algorithm implementation, you would be very well aware of who you are communicating with, their identity, with whatever way you would like to identify them. And I think rumor mongering and anti-entropy, the first two algorithms we looked at from L&D Myers, they were both anonymous because it wouldn't matter. You wouldn't necessarily need to identify the database in itself. You share the data itself. It can be from any site around the network, and you compute the deltas and you update your state in a way that you keep all the newer changes, and don't change things that you already know that you have the latest copy of, right? Nevertheless, they also studied both push and pull strategies, so that's something interesting to look at as well, and that helps you design system where you can rely on anonymous algorithms versus non-anonymous. The idea is here it helps because you do not have to necessarily, let's say, prepare an extra layer in order to identify, or you don't need to do some sort of special message signing in order to make sure that they are coming from a special known identity. Moving to the last category, error correction and no error correction. Here, it was very important to mention anything that is not anti-entropy, where you are not computing deltas of your current state with your replicas. You do not have guarantees that you would have consistent view throughout the network. So when you are using an algorithm like rumor mongering, there is always a non-zero probability that your messages would be lost. So you must have mechanisms in your system that would make sure that you achieve eventual consistency, and you must live with the guarantee of eventual consistency. You might not see all the updates in all the replicas as you expect in the time that you expect. That being said, there are a lot of practical implementations of Gossip protocol. I don't know if the discussions that we were having earlier with Grab, they also implement some sort of gossip protocols. But these protocols are used in IoTs. They are used in distributed ledger networks. I think 1 year ago we were discussing blockchain on the same platform, so they heavily rely on gossip protocols. The most classic use case is replicating your databases across different sites, which is what the original paper was about. And for us, it was a similar situation where we ended up using this. We had multiple sources of data that were supposed to be replicated in order to make sure that we have high performance downstream applications to provide them faster speeds of reads or to provide more scalability in the system. We ended up choosing a mixture of both anti-entropy and rumor mongering. So for a very critical section of data that requires strong consistency, we use at the moment rumor mongering. We use anti-entropy, make our transactions atomic, so the state only changes altogether or it doesn't change at all based on the delta that we have figured out. And for the places where we are comfortable with having some sort of weak consistency or eventual consistency, we choose rumor mongering. That means that the sources that we want to replicate, they communicate one change at a time. They don't send us the whole state. So they just send the message of state that has been changed. And then we internally state, and we also studied a little bit what time delta would imply, or what time delta can we use in order to make sure that our eventual consistency is more towards stronger consistency rather than eventual consistency. And then we optimized our system in order to make sure that the messages that are generated live in the system for that amount of time, like 72 hours or 36 hours, because that implies you are increasing the memory usage if you will keep messages alive for longer. If you keep the messages alive for lesser time, then you're increasing the probability of missing a message, right? So we found a balance between that time as well. There's more to be done. We must empirically study what would be a better, more optimized time. Right now, it's a heuristic. And the classification earlier helped us in realizing that for our specific problem, we wanted to go with something that is asynchronous. It provides no error, right? And in some cases, it provides error. Yeah. So that was the scope of the study, and I'm very glad to share today with you things that we
AJ,
did
we are
internally.
okay. Perfect. Yeah, I was trying to say that we are running out of time, but that's perfect.
Right.
Okay, so let's see if we have any question from the audience. I'm not sure if you can see them, and I'm afraid to change the camera because we'll mess up. Okay, so in what kind of product are you using these protocols, Gossip protocols and Epidemic?
So the product, when I mean product, it doesn't matter what product they are, but you can imagine it's a list of products that we must replicate. You have in your database thousands
It's
of
relating
products
with
that must be.
It's related with blockchain, or what kind of?
No. It's related to financial industry.
Okay.
So financial products that must be replicated through different sites because you have data centers in multiple zones. I mean, that's the most I can talk about the project. But the problem in itself, you can imagine, we can think of an e-commerce website, right? So they have a data center, let's say in Cluj, and then there's another data center in Bucharest, and both of them must have the same list of products. And you would need this kind of protocols to make sure that the list of products or the stock of products, the inventory of the products is consistent in both data centers, both in Bucharest and Cluj. It wouldn't make sense to direct requests generating near Cluj and send them to the data center in Bucharest, because obviously you have higher latencies in response, right?
Okay. Okay, we have a question here, Adrian.
Practically, I have two questions. So you mentioned that the events are stored for 24, 72 hours. So practically a short amount of time.
Yes.
And my question, what is happening if for various reasons one of the consumer are not able to read from the Kafka queue those events and practically are going to be desynchronized? Are you going to rationalize one of the replicated sites with the data in that case? So this is the first question.
Yes. That's the fallback mechanism, but the time we chose 72 reduces the probability of consumer not being synchronized to a very small time. And this is only for the part of products which we replicate using rumor mongering, meaning each event is a single change that has happened in the state of the database, right? You added a product, or you changed the product, you updated the product. So each event would be a message about that change rather than sending the whole database as a state.
Okay, and practically from what I see, the flow of the states is from one way to another and not vice versa. So practically you have only one source of truth, and with different view snapshots in the replicated database for I don't know, reporting purposes or things like that, right? So from that reason, my second question is, wasn't there available a solution already built having this kind of features? Was it necessary to build a custom one by yourself?
So again, this is, are you talking about distributed databases like Cassandra?
Exactly.
Is that the question?
So Cassandra
right.
can be one of those, but practically there are more than.
Right. So I don't have the view in the whole architecture of the company. I know since we work in banking industry, it's not a news that a lot of things are on legacy databases. So the sources that you see might be very old databases, right? And in case if you need to, what I have, and this is why it's anonymous, because I only have a partial view of the sources. I don't know what the machines are running in the back.
Okay,
right.
I understand. So you mentioned Cassandra, that means that it was a key value data store.
No, this is that's another thing. So there was no key value. We had to have some normalized form of data, otherwise downstream, I mean, relational data set. Otherwise, downstream applications that rely on the replications would have to change their implementation. That would trigger a very large change, right? So in the end, the part that we focused on was the synchronization. The constraint that we had was we had to replicate the fraction of the view that we see into a database technology, which is currently used inside the IT infrastructure that we work in, because downstream applications were relying on it. And earlier they only had one replica. So
get it. So it was a constraint to use a legacy database.
Yeah, and the replication was done using mailing, a similar concept as mailing. So you were out with 24 hours. And since we have now partial rumor mongering, the changes are migrated in 3 minutes. I know it's not as impressive as real-time things that you do in IoT, but it's from 1 day to 3 minutes. I think it's a massive improvement.
Okay, guys, if you want to talk more, I can help you connecting each other.
Right.
Okay, thank you, Ajay. It was great to see you again, and yeah, looking forward to see you next time.
Thank you very much as
Thank
well.
you.
Have a lovely evening. Bye bye.
Thank you. Bye.